Yeah, good morning, everyone. And let us welcome Professor Sumanta Tewari. Professor, I have the pleasant task of introducing him. Professor Tewari is presently an associate professor of physics and astronomy department in Clemson University. He obtained his master's from IIT Kanpur in 1997, and then he went on to do his PhD from UCLA. Completed his PhD in 2003. Then he had two stints of postdoctoral research, mainly connected with University of Maryland during the period of 2003 to 2008. And in 2008, he joined Clemson University as assistant professor of physics and astronomy. And today he is a tenured track associate professor of physics and astronomy in the same department. His research interests are broadly in theoretical condensed matter physics, topological superconductors, topological insulators, topological quantum computation, high temperature cuprate superconductivity, and topological states in ultra cold atom systems. He is an excellent researcher. You will be introduced to his style of teaching. We have had the opportunity to hear him once, and that is when I thought that it would be really nice if he can give us a tutorial for the students in this very specialized field of research, contemporary field of research. And practically, I would now give the floor to Professor Sumanta Tewari. Just before that, I want to announce happily that Professor Tiwari, will be joining our department of physics at IITD sometime this coming summer, like July, June, July. So, you all who are from IIT Delhi, you will have the opportunity to interact with him in person too. So, Professor Tiwari, now I will request you to come on the screen and practically see if you are connected and if you can share.
Yes. Okay. Um, Thank you, Professor Chatterjee, for the kind introduction. Let me just quickly mention that in 2008, it could be a mistake in my CV that I may not have updated, but in 2008, I joined Clemson as an assistant professor. In 2013, I was promoted to a tenured associate professor. In 2018, since 2018, I'm a full professor here, with tenure, of course. So I'm not sure, 100% sure if
Yeah,
the CV is up.
yeah,
Yes, if
in
the
your
CV is
CV it
updated.
was not there. I was thinking that in your,
Yeah.
when I saw your application, it was there as a professor. So I was wondering, why does it say associate professor? Then I thought maybe that is how I must have been mistaken. Sorry,
It could be.
sorry about
It
that.
could. No, no, no. It's okay. It could be that the CV that's there on my web page
Yeah, yeah,
is
that is
probably
there.
not updated.
Yeah,
Yeah.
yeah, yeah, that is
That's yeah. That's a minor. Yeah,
yeah.
that's okay. That's a minor issue. All right. So let me start by thanking Professor Chatterjee and the teams at Delhi and UK for inviting me to present these tutorials. So I'm going to talk about this sort of broad area of Majorana Fermions and topological superconductivity in condensed matter systems. Um, and as I discussed with Professor Chatterjee before, I'm going to sort of present this as sort of a tutorial in a classroom setting, meaning that I'm going to work out everything um, on a whiteboard instead of presenting just a PowerPoint presentation, which could have probably been easier. But I find from almost a year experience of teaching remotely that if I work out stuff on a whiteboard, it's probably going to be more engaging, and you'll probably profit more from the tutorial than just looking at equations and having me explain the equations. All right, so that's what I'm going to do, and so therefore let me see if I can share my screen. Um, yeah, share screen. Okay, uh, start broadcast. Okay, let me see if I. Okay, all right. Okay, so can you see my whiteboard now? It should be a white screen now.
Yes, sir.
Yeah.
Yes,
Okay.
sir.
All right, and you can um, so this is a sort of a vast topic, and because I'm taking this route of working out everything, I have to sort of move quickly. Although I'm going to work out everything, so if you're of course welcome to ask questions. But if I do not hear any questions, then I'm just going to move on. Okay, relatively fast.
Yes,
So do stop me if you don't understand something, and in in real time you can ask me questions. All
yes,
right, so
sir.
let us start. Okay, all right. So let us start with Majorana Fermions. What are Majorana Fermions? That is what I'm going to talk about first in a sort of qualitative way. Um, so to understand Majorana Fermions, we need to start from Dirac equation. Okay, so let's start with the Dirac equation. So we have Dirac equation, which is, of course, almost all of you know here. So I gamma mu del mu minus m psi equal to 0. So here the gamma mu are a set of 4 by 4 matrices, and there are 4 of them. Now, um, so the gamma mu matrices satisfy the following algebra: gamma mu gamma nu anti-commutator is 2 g mu nu, where g mu nu equal to 0, g mu nu equal to 0 if mu equal to nu, which means the gamma matrices are anti-commuting. So these are 4 by 4 anti-commuting matrices, and there are 4 of them. Um, so typically in one, the conventional gamma matrices are, for instance, the one that Dirac took was gamma 0 is sigma 3 cross identity, and gamma j, where j equal to 1, 2, 3, are I sigma 2 cross sigma j. So as you can see, this is a real matrix, and I sigma 2 is a real matrix. So depending on what the value of j is, gamma j could be real, a real matrix, or an imaginary matrix. Which means now if you look at this equation, the Dirac equation, because some of the gamma mu are real matrices and some of the gamma mu are imaginary matrices, the Dirac equation is basically a set of 4 coupled differential equations with real or imaginary coefficients. All right, so this is a complex, so set of 4 complex coupled differential equations. So in general, therefore, if you get a solution psi, which is now going to be a spinor, it's a 4-component column vector, then psi x, psi star x is a distinct column vector. Okay. Now there is an operator called charge conjugation. So under charge conjugation, operator, you take psi and it goes to psi star. So if you have a solution of the Dirac equation, it's a 4-component column vector. Generically, under charge conjugation, you get a distinct column vector. Okay, and this is what describes an ordinary electron. Now, because the charge conjugation changes the column vector, when you do second, so all of this is first quantization. When you second quantize, then of course you treat the solution of the Dirac equation as a field operator. Okay, you elevate the status of the psi from a wave function to a field operator. Then your psi becomes a field operator. And because of this property that charge conjugation gives you a distinct column vector, you have psi x and psi dagger x. And these are, of course, two distinct operators. And one you consider as a particle. So if psi dagger x creates a particle, then psi x annihilates a particle, um, and so forth. Okay, or you can think of psi x as creating a hole. Okay, all right, and these are two distinct operators. Now, and the other property that I have been mentioning is that charge conjugation gives you a distinct column vector as a solution of the Dirac equation, which means that charge changes. So particles and holes have opposite charges. Now, at the time when these things were discussed by Dirac and others, neutrinos, the concept of neutrinos came about by Pauli was the one who proposed the concept of neutrinos in beta decay experiments. And from charge conservation, it turned out that neutrinos do not have charge, even though they are fermions, like electrons. So, so therefore, you need a solution of the Dirac equation. Yes, well, is there a question there?
Yeah, yes, Sumanto, actually, somebody is asking you question. Maybe they do not see in the chat box. Should it be when mu is not equal to nu, G is equal to 0?
Sorry, say it again.
Yes, I have actually written that they can unmute and ask the question directly also. So
yeah,
that
you
will
can ask the
better.
question directly.
Okay.
Sure. So what is the question?
So the question is, should it be when mu is not equal to nu, then whether G is equal to 0? So
no. So then G is the Minkowski matrix. It's not quite important because G mu nu is a Minkowski matrix, so it goes as 1 minus 1 minus 1 minus 1. Sorry, G mu nu equal to 0 when mu is not equal to nu. You're right. I forgot about this. So that's an error. Is that what you're saying? G mu nu equal to 0 when mu is not equal to nu?
Actually, it was asked by Liu Yang. But
no, so he says yes.
And I thank whoever asked this question. That was an error on my part, and I'm hoping that with time I'm going to stop making those mistakes. But so yeah, you are right. So G mu nu equal to 0 when mu is not equal to nu, and when mu is equal to nu, then you have is 1 minus 1 minus 1 minus 1 depending on what the value of mu and nu is. All right, now so therefore okay, so I was talking about neutrinos. So neutrinos clearly do not have charge. I mean, so that is something that people understood from electric charge. I'm just giving you a little bit of history of what Majorana Fermion, how Majorana Fermion came about. So neutrinos were thought to have no charge. They still are thought to have no charge, and that follows from electric charge conservation in beta decay experiments. So therefore, you need some mechanism within Dirac equation to describe a neutral fermion. Okay, something whose wave function does not change under charge conjugation operation. So if a wave function does not change under charge conjugation operation, remember charge conjugation takes from the particle to an antiparticle. It also changes the charge. Okay, so if something does not have charge, then charge conjugation operation should not change the wave function. Okay, now as I told you, the charge conjugation operation essentially is just complex conjugating the wave function. So if the charge conjugation does not change the wave function, which means you need the wave function to be purely real. Okay, So how can you have a wave function solution of the Dirac equation which is purely real? I mean, that does not seem to be very easy to do, be very easy to get, because the differential equation itself has complex coefficients. I mean, the set of four coupled differential equations have complex coefficients. So Majorana first thought about a solution, or gave a solution to this problem. What Majorana said is that it is actually very simple. So he said that the only constraint on Dirac equation is really this algebra. Okay. Now he found a representation of the Dirac matrices, 4x4 matrices, that satisfies that algebra, but at the same time, all four of the matrices are purely imaginary. Okay, the conventional Dirac matrices, some of them are real and some of them are imaginary. But Majorana found a representation of the Dirac matrices that satisfy the same algebra, but they are purely imaginary. So for instance, Majorana found that if you write gamma 0 equal to 0, 0, sigma 2 and sigma 2, and gamma 1, which is as I sigma 1, and 0, 0. So these are 4x4 matrices because sigmas are 2x2 matrices. And gamma 2 is 0, 0, sigma 2 and minus sigma 2. And gamma 3 equal to I sigma 3, and 0, 0. These four matrices will satisfy the same algebra, the algebra of the gamma matrices. But at the same time, as you can see yourself, because there are so many gamma 2s here, and wherever there is gamma 1, you have a factor of I there, and gamma 3, you have a factor of I there. These matrices are all purely imaginary. Okay, all entries in these matrices are purely imaginary. Now, if you look at the Dirac equation, okay, because of this factor of I that sits here, and the gamma mu's are purely imaginary matrices, Dirac equation, these 4x4, these four couple differential equations now all have purely real coefficients. Okay, so therefore you are allowed to have a purely real solution. Okay, so that was Majorana's contribution. So he found a representation of the Dirac matrices so that you get a solution psi which is purely real. Okay, so therefore under charge conjugation you get a psi star which is nothing but psi itself. Okay, and he did this purely to explain the occurrence of neutrinos which are charged neutral fermions. Now there's a further consequence of this. Typically when you quantize Dirac equation, when you second quantize Dirac equation, okay, what you do, as I said before, you elevate the status of these first quantized solutions, which are wave functions so far. You elevate their status to becoming field operators. Okay, field operators means now we have creation and annihilation operators. So typically with Dirac solutions, psi xd, now you are treating them as field operators. You second quantize them using, so s is spin in the index, and then you write d3p by 2 pi cube, and then you introduce these operators bsp. Now b's are operators and usp's are functions, spinors basically, e to the power ipx plus ds dagger p, and then vsp, these are spinors, e to the power minus ipx. This is how you second quantize Dirac solutions psi. So b's and b, so this is an operator, that's an operator. This is a 4-component spinor, this is a 4-component spinor, and of course this is a 4-component spinor. But now this 4-component spinor is a field operator. All right. So what this equation means basically is that this B is now a particle annihilation operator, and this ds dagger is a hole or anti-particle creation operator. Okay. you don't have to really get into the details of this. Just follow what I'm saying here. Now, imagine that you got a solution psi using Majorana's method, which is purely real. Okay, so then if you want to second quantize the Majorana solution in exactly similar manner, then S is still the spin in the spin index. Then you have to write d3p by 2 pi cube, and then you have BSP USP e to the power IPX. But now you have to write the same BS dagger P, and then this VS you can write as VSP e to the power minus IPX. But because this psi M has to be a real solution, you must have VSP is US star P, and previously you had B there and DS. So these are two different operators, but now you have to use the same operator. Otherwise, this field operator psi will not be real or Hermitian. You know, since you have elevated it to be a field operator now, psi must be equal to psi dagger. So therefore, you need this BS, and over here you have BS, and over here you must have BS dagger. The same operator. So now a particle annihilation operator, if particle annihilation operator is BSP, then the whole creation operator or antiparticle, so let me Dirac call them antiparticle, so let me call it antiparticle. So antiparticle creation operator, previously it was a different operator D, but now that's BS dagger. Okay, P is of course momentum. So you can see the antiparticle creation operator is BS dagger, but particle creation operator is also BS dagger. Okay, that follows from here, that the particle creation operator must also be particle creation operator is also BS dagger. Okay, and that follows from the reality of the solution of the Dirac equation psi. All right, so what this is telling us is that what started with Majorana trying to describe a charge neutral fermion also leads naturally to the fact that the particle creation operator is the same as the anti-particle creation operator. Okay, so this leads to the identification that Majorana fermions are fermions where particles are same as the antiparticles. Okay, so you'll hear this phrase number of times, that the particles are the same as their own antiparticles, and this is the origin for that when you second quantize the Majorana field operator, you have to introduce particle creation and antiparticle creation operators which are identical. Okay, so therefore we find that the defining property of Majorana fermions is that, so now I'm going to use a different notation. Instead of B and B dagger, I'm going to use the notation gamma, okay, for the second quantized operator representing a Majorana fermion. So the defining property of Majorana fermions from high energy physics that we find is that we must have gamma dagger equal to gamma and charge neutrality. They must be charge neutral. Okay, so this is very different, by the way. This relation is very different from ordinary fermionic creation and annihilation operators. There, of course, C is not equal to C dagger, and in fact, you have the fermion anti-commutation relation where C dagger C is equal to 1. Okay, that's not true for gamma and gamma dagger. Gamma and gamma dagger are in fact identical operators. So, but these are still fermions. Majoranas are still fermions. I mean, that follows from imposing fermionic anti-commutation relations on the field operators over here. I'm not going into the details of how the fermionic the algebra is derived in the Dirac equation. But if you follow the same steps as one does in the Dirac equation, you'll find that for Majorana fermion, if you have more than one, so over here I had just one, but let's say if you have more than one, and I can write them as gamma I and gamma j, then I'll have gamma I comma gamma j dagger, okay, which is the same as gamma I comma gamma j, because gamma j dagger is same as gamma j. It is 2 delta ij. So this is fermionic anti-commutation relation. It's just I have a factor of 2 instead of 1 here. That's just convention. I mean, that's, you can just normalize the Majorana operators or wave functions in a way so that you get a factor of 2. But some books also use 1 there. So what this is saying is that when I equal to j, then you have a 2 on the right side. But when I is not equal to j, then the gamma I and gamma j anti-commute. So when I is equal to j, then of course this anti-commutator gives you 2 gamma square or 2 gamma I square, which is 2, and that gives you gamma I square equal to 1. So it is to get this gamma I square equal to 1 instead of half. This is why sometimes we take normalization such that you write a factor of 2 on the right hand side. But nothing really changes if you write 1 to be consistent with this fermion anti-commutation relation here. All right. So therefore, the algebra that defines Majorana fermions are basically gamma dagger equal to gamma, and gamma squared equal to 1, and gamma I comma gamma j is 2 delta ij. Okay. This formula is also very different from an ordinary fermion, because if you recall, for an ordinary fermion, c square is actually equal to 0. Okay. I hope you remember that. You cannot create or destroy 2 fermions with the same quantum number. All right. Now, so far we talked about charge neutrality. Okay, charge neutrality and particle is the same as its own antiparticle. These 2 properties are not uncommon among bosons. For instance, photon is a common example. Photon, which is a boson, has those properties, but these properties are actually extremely rare. In fact, charge neutrality itself is extremely rare for fermions. Neutrinos seem to be one candidate. Initially, of course, they were thought to be wild fermions because they thought to be massless when they were first discovered or first proposed in the 1930s. But then people figured out that neutrinos do have a small mass, but they're still chargeless. So whether neutrinos are Majorana fermions, meaning that neutrinos and antineutrinos are same or different, whether antineutrinos exist in nature, or neutrinos are Dirac fermions, such that they do have antineutrinos, this issue is still not settled. Okay, so the status of Majorana fermions in the high energy physics is still not found. There has been no firm conclusion about the status of neutrinos. On the other hand, we now talk about Majorana fermions in condensed matter. Now, in condensed matter, of course, the constituent particles are still electrons and ions. Those are the things that we work with. So Majorana fermion cannot be a fundamental particle in condensed matter. So when we talk about Majorana fermions in condensed matter, we mean quasi-particles, okay, or excitations. Now, in condensed matter, therefore, you have, we talk about, in condensed matter, we talk about Majorana quasi-particles. Majorana quasi-particles. As excitations of some underlying many body state. Now, in condensed matter, the definition of Majorana fermions are somewhat more restrictive. Okay, They are chargeless, so charge neutral. They are also massless and spinless. Okay, and in fact, in condensed matter, Majorana fermions are thought to have no internal quantum number, no non-zero internal quantum number. These are all internal quantum number, charge or spin, or these are all internal properties. So Majorana fermions are thought to be devoid of any non-zero quantum number for any of the internal observables. And there are two other properties for Majorana fermions that we're going to get into later on. These are topological protection. Topological protection. I'm just listing some of the important concepts that people talk about, and one need to really know what they mean, and non-abelian statistics. So I'm going to talk about that hopefully by the end of today's tutorial. All right. Now, in contrast, of course, in high energy physics, these concepts are not there. In high energy physics, the only thing that we talked about were charge neutrality and the particle being same as their own antiparticle. And of course, Majorana fermions in high energy physics do have mass. And of course, they follow fermionic statistics. There is no non-abelian statistics in high energy physics. And there is no topological protection or any of those things in high energy physics. All right, I'm going to talk about why in condensed matter we talk about these additional restrictive properties and why they're useful later on. All right, now the question is, where in condensed matter can we find it? We can look at our conventional systems that we think about in condensed matter, for instance, metals and semiconductors. What are their excitations? Well, in metals, we have particles and holes, and in semiconductors, we have particles and holes. And clearly, they are charged excitations, both particles and holes, so they cannot be Majorana fermions. How about exciton in condensed matter, which is a bound state of a particle and a hole? That seems to be chargeless, but unfortunately, it's a boson, so it cannot be a Majorana fermion. And in fact, superconductors in condensed matter seem to be a natural platform for hosting Majorana fermion, because in a superconductor, the very concept of charge loses its meaning, because, you know, as most of you know, that superconductor charge is no longer conserved because the gauge symmetry is broken. The consequence of that is that the quasi-particle in a superconductor is a superposition of a particle like object and a charge and a hole like object. So it's a superposition of both. So charge is no longer a good quantum number. But even in superconductor, getting a Majorana fermion is actually very hard, because typically, if you look at an S-wave superconductors, the superconductor quasi-particle operator can be written as U C up dagger plus V C down. Okay, that's a typical Bogoliubov quasi-particle. So if you take the corresponding D, then you get U star C up plus V star C down dagger. So if D has to be equal to D dagger, then you need, you just compare the two operators. Then you need, so this one, the one that does not have dagger, you have to compare with this. So first of all, you need U star equal to V, and V star must be equal to U, or which is the same as this. So you need this, okay? This is possible to get, because as you know, I mean, U becomes equal to V on the Fermi surface. So that's where the zero energy stuff is coming from. So you need this U equal to V, and U equal to V actually happens for a superconductor exactly on the Fermi surface. But even if you are restricting yourself to be exactly on the Fermi surface, meaning you have a superconducting quasi-particle, approaching the Fermi surface or approaching zero energy. But you still see that there is a complication that comes from the spin, because you have this undagger here has an up spin. The undagger operator here has a down spin. So even if you restrict yourself exactly on the Fermi surface, you are not going to be able to satisfy D equal to D dagger in a superconductor.
Professor Tewari, can I ask a question?
Sure.
So please re-articulate the argument that you offered. I mean, why is superconductor, gauge symmetry breaking is a more natural choice of finding Majorana fermions? And these three, and the equation that you have written. Just repeat that argument again, please.
Sure. So I said that charge neutrality is one of the precondition to get a Majorana fermion as a quasi-particle in a condensed matter system. Now I gave you a few examples of quasi-particles in a condensed matter system, and they fermionic quasi-particles, and they seem to all have charge, particles and holes and so forth. On the other hand, in a superconductor, the very concept of charge breaks down, because as you can see in a superconductor, the gauge symmetry is broken. Gauge symmetry is conjugate to the charge quantum number. But even if you ignore those technicalities, if you look at the typical operator for the quasi-particle in a superconductor, these are the Bogoliubov operators. Okay, you see that it has a component which goes as C up dagger. Okay, this is a particle creation operator. So this operator creates a fermion, creates an electron. Okay, so this part of the superconducting quasi-particle operator is associated with charge +1 or +E. This part, on the other hand, destroys a particle. This is the annihilation operator, C down. Okay, so it destroys an electron. That means it creates a hole in the system. Okay, so this part of the operator of the Bogoliubov quasi-particle operator is associated with a charge -1 or -E. Okay, so this entire operator, D dagger, does not have. So this is no longer a charge eigenstate. So if you have a D dagger operating on the superconducting vacuum, this state is not a charge eigenstate, because this operator itself does not have a single charge quantum number. Okay, it's a superposition of two pieces, each one of which has a different charge quantum number. You can contrast this with the spin quantum number. Here you are creating an up spin, and here you are destroying a down spin. Now, destroying a down spin is equivalent to creating an up spin. So this operator, therefore, has a spin quantum number, which is +1. Okay, but it does not have a charge quantum number. This is not a charge eigenstate. This state is not a charge eigenstate, which means that if I have to find some sort of a Majorana quasi-particle which is charge neutral, okay, superconductor might be a possibility, because the charge itself is not a good quantum number in a superconductor. I'm not saying it's any guarantee that, because the very concept of charge breaks down for a superconducting quasi-particle, that does not mean that there's a guarantee that there'll be Majorana fermion. I just showed you by illustrating that if this is a Bogoliubov operator in a superconductor, then D dagger, then you can write D, and you can see that these two operators are clearly not the same, because even if you impose the condition that your U star is equal to V, okay, you have a C up here as the undaggered operator, and you have a C down there. So down meaning down spin. So these two operators are clearly not the same. So therefore, D and D dagger are not equal. D and D dagger are not equal. If you have still doubt or confusion regarding what I'm saying, just imagine that you did not have these spins here. Okay, these spin indices. Suppose I write down the Bogoliubov operators as d dagger equal to c up dagger, d dagger equal to u c dagger plus vc. There is no spin index anymore. I got rid of the up and down spin indices. Then d would have been simply u star c plus v star c dagger. So now if I impose the condition that u star equal to v, then you can see that this part is identical to that, and this part is identical to that. So then you'll have indeed d equal to d dagger. Okay, that kind of identification you cannot do if you have these spins, with your operators. Does that make sense?
Yes, it does. But I mean, Cooper pairs in the quasi-particle are associated with some kind of spin.
Yes.
Can you negate the spin and say just because charge conservation is not required? I mean, in actuality, the spin is associated with Cooper pairs.
Yeah. So you're absolutely right. So therefore, this is what I said, that even in superconductors, getting Majorana fermion is hard because there is always spin. Because there is spin, and spin complicates matters. You cannot really get d and d dagger which are equal even in a superconductor. I mean, this is the status. I mean, this used to be the status until about 6, 7, 8 years ago, that even in superconductors, naturally occurring superconductors, you cannot create Majorana fermions. Of course, that's where people used to talk about spinless superconductors. Okay, so you just artificially remove the spin index, and then of course you can talk about Majorana fermions in a spinless superconductor. But the idea was, the problem was, can you somehow make a special kind of superconductor in which you can somehow manage to get d equal to d dagger? And that seems to be a problem, which is a problem that I solved with some of my collaborators at University of Maryland. That indeed you can create a special kind of superconductor in which you can satisfy d equal to d dagger. Okay, but not any ordinary superconductor, naturally occurring ordinary superconductor will not give you d equal to d dagger. Okay, I mean that's something I'm going to. So what the system is, and how do you get d equal to d dagger in a sort of artificially created superconductor? We are going to talk about that in the next tutorial. But I'm just giving you the background and motivating the problem.
Just a quick question. So the topological superconductor, like say strontium integrated bismuth selenide or copper integrated bismuth selenide, are those the compounds where d equals to d dagger? I mean, is that the mechanism, or there's something else? I mean, the experimentally achieved topological superconductors, do they satisfy this d equal to d dagger requirement?
Yeah, I mean, yes and no. I mean, there are so the system that I alluded to before, that is of course a topological superconductor. Copper dope bismuth selenide, you mentioned that. So all topological superconductors will have Majorana fermions as the boundary modes. Okay, not their bulk quasi-particles, but on their boundaries, they will have Majorana fermions. Now, whether or not those Majorana fermions are localized and extended, that creates an additional complication. So for topological quantum computation, what you need is localized Majorana fermions. I'm going to talk about those as well. But yeah, I mean, topological superconductors are the candidates that will have Majorana fermions as their quasi-particles localized at the boundaries and at vortex cores, okay, but not at the bulk. So you need to have some sort of a defect in a topological superconductor and localize quasi-particles at the defects. So if you have a defect in a superconductor, typically those defects will trap fermionic excitations, and those excitations will turn out to be Majorana fermions, satisfying this property d equal to d dagger. Okay, and those defects are either vortices or the boundaries. Okay, all right. So I'm going to talk about those in more details. I mean, the practical realization of experimental systems and how you can actually create Majorana fermions, hopefully in the next tutorial. All right, so let me give you a little bit more intuitive understanding of what Majorana fermions are. So suppose we start with so far so let me just make one final comment. So this is why because of this reason that even in a superconductor it's kind of hard to get Majorana fermions or D equal to D dagger because of this mixing between spins, up and down spins. This is why people talk about spinless superconductors. Okay, I mean, you may or may not have heard about this, but spinless superconductor is a very common system that people study when they first learn about Majorana fermions. And this is the reason that in a spinless superconductor, if you can create quasi-particles which lie exactly on the Fermi surface, which ensures this condition, this V star equal to U, if these are real, then of course V equal to U, and V equal to U is satisfied exactly on the Fermi surface for a Bogoliubov quasi-particle. So if you can somehow get a zero energy quasi-particle in some sort of a spinless superconductor, then you can get Majorana fermions. Okay, now that zero energy quasi-particle is also hard to get exactly at zero energy. You typically do not get a quasi-particle excitation in a superconductor exactly at zero energy or exactly at the Fermi surface. There are some special kinds of superconductors, namely Px plus Ipy. The order parameter has to be P plus Ip or Px plus Ipy. That will allow you to have an excitation or quasi-particle exactly at zero energy. But I'm going to come to those questions towards the later part of the tutorial. Before I do that, let me sort of motivate the concept of Majorana fermion a little bit more, and draw some analogy and draw some sort of schematic pictures of what Majorana fermions are. So suppose I have a very ordinary quantum system, a delta function potential. So all of you have looked at the delta function potential and its solution, the solution of the Schrodinger equation with delta function potential. The Hamiltonian is clearly it's simple. So it's minus alpha delta x, alpha greater than 0. So it's an attractive delta function potential. So the solution is psi x. Okay, it's something like square root m alpha by h bar square, and then exponential minus mod x divided by xi. Okay, so you have the delta function potential. The wave function looks like this. The wave function looks like that. Okay, and it's a bound state, and the corresponding energy eigenvalue. So eigenvalue energy is given by minus m alpha square by 2.
Can I ask one question?
Sure.
Sumanta?
Yes, go ahead.
Yeah. So I just wanted to be very clear about the identification of topological superconductors. So you are saying that a topological superconductor must have a Majorana bound state, right? That's what you said.
Yes.
Now you said that is only on the edge. Is that right? I thought it is. Superconducting bound state inside the gap. Is it at the edge or also in the bulk? I mean, what is a criterion of?
Well, anytime you have, so in the bulk also you can have order parameter defect. You need to have a defect to have a localized bound state in a superconductor.
Right.
So in the bulk also you can have a defect. For instance, vortices are defects in the bulk.
Okay, right.
Vortices are excitations in which the order parameter goes to 0, delta goes to 0 at the vortex core. Right, So just as the edges or the surfaces are places where the order parameter goes to 0, I mean just outside the surface. Similarly, vortex can also be, vortex is kind of like an edge because it creates a circle inside which the order parameter again goes to 0. So you can think of the inside of a vortex as, some sort of a vacuum outside.
Right. So if you have bulk superconductivity, then you don't have Majorana bound state. Is that what you were?
I mean, you will have conducting Majorana states, not bound states.
Conducting Majorana. Okay.
Yeah.
So what is topological superconductors as such? Because you started off with Majorana mainly, and you are, of course, it is. I mean, what you are saying is right that if you can find Majorana, then it has to be topological superconductor. But is there? I mean, can a topological superconductor evade Majorana?
No, the excitations of topological superconductors have the property that gamma E dagger equal to gamma minus E. Okay, which means that if you can create a zero energy quasi particle in a topological superconductor, this will satisfy gamma dagger equal to gamma.
And that is possible only in a defect.
Bound state, Majorana bound state. Because bound states, when you talk about bound state, you mean a localized state.
Right.
So in order to have a localized state, you need to have a defect in the bulk or on the edge.
Okay.
Otherwise, you'll have conducting Majorana states. Okay, I mean, so the states which will satisfy this condition. This is kind of like a Majorana condition, but not exactly. These are not particles exactly equal to their antiparticles. I mean, these are not gamma dagger equal to gamma. These are gamma E dagger equal to gamma minus E. Okay, so this would be the property satisfied by all the quasi-particles in a topological superconductor. But only when E becomes equal to 0, if you can get a quasi-particle exactly at 0 energy, those are the ones which will satisfy gamma dagger equal to gamma. And that typically happens in a superconductor if you can create a 0 energy bound state. Okay, I mean, this is another problem that you may have seen before, that if you have some sort of a defect in a superconductor, those defects trap localized states, and sometimes the energy of those localized states can go to 0.
Right. Okay. I mean, that happens for vortices and also with disorder of certain kind. Yes. I mean, this Caroly matricon states and things like that, they can have energy. Yeah.
Exactly right. That's exactly right. Now I'm going to talk about Caroly degen matricon states also, hopefully in today's lecture. In ordinary S-wave superconductors, you normally do not get 0 energy states inside the vortex core.
Very small energy. So
right. I mean, you'll have the lowest energy state in the vortex core will have energy delta squared by epsilon F, which is small but still finite. Okay.
Just one line I want to offer, Professor Tewari. What Amit is asking. I mean, so I'm sure you will cover that in the next tutorial, topological superconductivity. But experimentally, what is now being it's understood now. Suppose you take strontium bismuth selenide or copper bismuth selenide. So the core, the bulk interior remains a gapped, typical could be S-wave superconductor. If you want to find topological superconductivity, it has to be on the surface. So without even having defects, the question that Amit was asking, if you have a bulk material and you want that for some theoretical reason, topological superconductivity can be realized, spinless or not, that's a separate issue. But then the bulk remains a gap superconductor. It's a S-wave superconductor. And the PX plus IPY features would be basically confined to the surface. So those are the places where probably you can find more Majorana. So the answer is, even if you have a bulk superconductivity without defect, these Majorana modes can only be seen only on the surface, and the order parameter of PX or IP plus IPY can be realized only on the surface, not on the bulk. That was my just addition. Maybe we'll revisit this when you discuss topological superconductivity. Without vortices, topological superconductivity can be realized in bulk materials as well, but only as surface states.
Okay. Let me not get into those points right now. I mean, I could start discussing those right now, but then we'll not finish this what I planned in today's lecture.
Yeah,
But
please,
all of
please
you,
go ahead. Yeah,
but all of you are
yeah.
right. But I'm going to talk about those things in more detail, hopefully in the next tutorial, experimental realization and so forth. But you're right. I mean, that statement I agree with, that in a topological superconductor, if you do not have vortices and so forth in the bulk, there is still an order parameter defect. I mean, you can think of the surface or the edges as defects in the system, because those are the places where delta goes to zero right outside. Okay, so the surfaces will host Majorana fermions, or Majorana conducting Majorana fermions, because these Majorana fermions will then be all over the surface. Okay, in order to have local Majorana fermions which are localized in all directions, you need a point defect. Okay, I'm going to come out. I'm going to discuss those later, hopefully in the next tutorial, when we talk about experiments and so forth. All right, so I was talking about this delta function potential, and as you know, if you have a one-dimensional delta function potential, then you have exactly one bound state. This is an example of a bound state or localized state. This is a state which is localized at that. You can think of this as a defect. Okay, defect which creates this potential well, and you have exactly one bound state with an energy minus epsilon. Okay. Now, this is first quantized description. How do you describe such a system in second quantization? Well, in second quantization, you talk about Fock space, meaning the particle numbers. Particle numbers become important. Occupation numbers. So for this system, the delta function potential, you can start by defining this state, which is empty. Okay, this state has energy equal to 0. And you can define the other state, which is 1, and this state is nothing but C dagger 0. So you have created a particle in this wave function, in this state, and this state has energy E equal to minus epsilon. Okay, and also you can define the annihilation operator. So C1 is equal to 0. So that's a very simple Fock space description of a single fermion, single electron. Now, clearly, I can define gamma 1 equal to C plus C dagger, and gamma 2 equal to C minus C dagger divided by I. Okay, and you can check. I mean, this is by construction. It's kind of obvious that gamma 1 dagger equal to gamma 1, and gamma 2 dagger equal to gamma 2. Okay. And you can also check that gamma 1 square, which is C plus C dagger, and times C plus C dagger. So that's C square, which is 0. C square is 0 for fermions, plus C dagger, plus C dagger C, plus C dagger square, which is also 0. So that gives you C dagger plus C dagger C, which is 1 for a fermion. So gamma 1 square equal to 1. And similarly, you can show that gamma 2 square is equal to 1. And you can also show, and I'm not going to do it, but it's straightforward, gamma 1 anti-commutator gamma 2 is equal to 0. So you have, just from this very simple one electron system, we have two Majorana fermions. Okay. And you can do everything that we do with Majorana fermions here. You can define the occupation number is C dagger C, of course. That's the occupation number of the fermions. You can from these formulas, from these definitions, this is I can invert those equations, and I can get C equal to 1 by 2 gamma 1 plus I gamma 2, and C dagger equal to 1 by 2 gamma 1 minus I gamma 2. Okay, I mean I've just inverted these two equations. So you just add both sides. I mean add gamma 1 if you do gamma 1 plus gamma 2, gamma 1 plus I gamma 2, then you're going to get 2c, and therefore c is this, and c dagger is that. And you can use this to write your occupation number. And if you do the algebra, it's going to so it's 1/4 gamma 1 plus I, or gamma 1 minus I gamma 2, that comes first. So it's gamma 1 minus I gamma 2 times gamma 1 plus I gamma 2. And I'm not going to do the next steps, but you can keep on using, gamma 1 square equal to gamma 2 square equal to 1, and gamma 1 gamma 2 equal to minus gamma 2 gamma 1, and so forth. And you will be able to show that this is equal to half of 1 plus I gamma 1 gamma 2. So you have I gamma 1 gamma 2 equal to 2n minus 1. Okay, so this is 1 for n equal to 1, and this is minus 1 for n equal to 0. Okay, so I gamma 1 gamma 2, this operator I gamma 1 gamma 2, this basically counts, depending on the value to be 1 and minus 1, it counts the fermion parity. Okay, fermion parity means basically the number of fermions is odd or even. So this is called fermion parity operator. And you'll see this term come about again and again, fermion parity. All right, now we can also, what is the second quantized Hamiltonian? Hamiltonian is, for this simple system, is minus epsilon c dagger c. This basically says that if you have an electron in that localized state, localized at the delta function potential, then the energy is minus epsilon. If you do not have an electron, then of course the energy is 0. So again, you can use these definitions, C and C dagger, in terms of gamma 1 and gamma 2. And so C dagger C, so it's going to give you minus I epsilon by 2 gamma 1 gamma 2 plus gamma 1 gamma 2 plus constant. You can check those. So we have everything that we need. We have a Hamiltonian that has a pair of Majorana fermions. We have fermion parity. We have gamma square equal to 1, and all the algebra and everything. So what is the big deal? I mean, why people talk about so much difficulty in obtaining Majorana fermions? The problem here is that these two pair, so this pair of Majorana fermion, gamma 1 and gamma 2, they are describing the same fermionic quasi-particle. So these are like quarks. I mean, they are on top of each other. They are in a bound state in this electron. Okay, they do not have separate identity. It's basically kind of like coordinate transformation. When I went from C and C dagger to gamma 1 and gamma 2, I am describing the same electron in a different coordinate system. Instead of C and C dagger, I'm using gamma 1 and gamma 2. So these Majorana fermions, therefore, are occurring in pair. The question is there a way that I can somehow separate these Majorana fermions spatially? If I could separate Majorana fermions, these two Majorana fermions spatially, then these would be non-degenerate zero energy states, okay, which have these Majorana properties. And those are the ones that will have those interesting properties that I talked about before: topological protection, non-abelian statistics, and so forth. If you have a pair of them in a bound state and you cannot separate them, those are not Majorana fermions. Those are ordinary fermions. You're just describing the ordinary fermion in a different coordinate system. All right. So I talked about Um, Previously, I talked about
Hello, excuse me, sir.
spinless. Yes,
Can I ask a question?
sure.
Sir, you mentioned that one of the properties you want is that one of the cases that its gamma dagger should be gamma,
Hmm.
and these occur at zero energy modes in superconductor. But
Right.
now you're referring to a non-degenerate bound state. I mean, shouldn't that, if they're both zeros energy states, then in fact degenerate?
Yeah, you are right. I mean, you're absolutely right. That's slightly abuse of language. What I meant is you have a Majorana fermion occurring here, so that is a zero energy state, zero energy quasi particle of the Hamiltonian, and there is another Majorana fermion that occurs far, far away. So, so in that sense, yes. I mean, if you have a system where you have uh, spatially separated Majorana fermions, those must occur in pairs, and therefore if you took the Hamiltonian of the system and exactly diagonalized, you will find a pair of zero energy eigenvalues. When I said non-degenerate, I what I meant is, there is no other zero energy state nearby here.
Okay. Yeah.
Okay, as opposed to this case here, where both Majorana fermions are sitting on top of each other. They are both at zero energy and they are really in a bound state.
Okay. Sure. Thank you.
Okay, all right. Okay, now I talked about spinlessness. I said that spinlessness is a requirement. Some sort of spinlessness is a requirement. And if you have, somehow, if you can conceive of a spinless superconductor, you can get such localized, again, I mean, so zero energy bound states, which have Majorana fermionic second quantized operators, spatially separate from each other. So let's look at an explicit solution for a system like that. So let's look at 2D spinless px plus IPY superconductor. I mean, excuse my handwriting. I mean, it's so this is still writing on the computer. So if something is not understandable, do ask me about it. All right. So 2D spinless PUF superconductor. So the Hamiltonian for 2D spinless PUF superconductor. So I'm going to give you an explicit solution. This is something that you do not normally see in the literature. People just talk about 2D spinless PX plus IPUF superconductor, and they talk about in the continuum model and do all kinds of approximations and motivate that this system will have Majorana fermion. But I'm going to give you an explicit solution of such a Majorana fermion state. So so H, the Hamiltonian, is integral d2x prime and psi dagger x. These are fermionic fields, H x prime and psi x prime. This is from a paper that I wrote some time ago. The Sarma, Nayak, Zhang, and Peter Zoller. So this is PRL 2007. I haven't seen too many places where this type of a explicit solution is given, not even in books. All right, so this is the Hamiltonian where psi dagger x is Cx C dagger x. That's the Nambu row, and psi x is C dagger, or psi x prime is C dagger x prime and Cx. And H x prime is, you have this kinetic energy term minus delta square by 2m minus mu and then delta x minus x prime sigma z plus delta xx prime by 2 sigma plus. And I'm not going to write down everything. Of course, there is not enough time. But let me just write down the Hamiltonian, sigma minus. So sigma plus is, of course, sigma x plus I sigma y, which is 0, 0, 0, 1. And you can see that this delta appears as one of the off diagonal. And that's why there's a factor of 2, because this is this 2 here. And sigma minus is sigma x minus I sigma y. And that's 0, 0, 0, and 2 here. All right. So for px plus ipy state, when the order parameter is px plus ipy, so in this state, we take delta p to be delta 0 times px plus ipy. It's as simple as that. You can have a pf here just to make it dimensionless. All right. Now, I said that, so this is a Hamiltonian for a 2D spinless px plus ipy superconductor or superfluid. Now, I said that you need an order parameter defect to have a localized zero energy state, a Majorana bound state. So let's take a vortex, a single quantum vortex. So you take delta p to be delta naught by pf times e to the power I theta by 2 px minus ipy and e to the power I theta by 2. I mean, it's just written like this, but the total phase is, of course, theta now, and we will work in the rho theta polar coordinate system. So the total phase is e to the power I theta, and so that's so phi, the phase of the superconductor order parameter, is basically theta. So if you go around in a circle, then theta changes by 2 pi, and therefore phi changes by 2 pi, and this is the model of a vortex. I mean, this along with the fact that I'm going to take delta 0 to be 0 for rho less than some coherence length xi, and delta 0 equal to delta 0. Well, I mean, it's not equal to 0 basically. Yes, just this is fine, and equal to delta 0 for rho greater than xi. So this would define the vortex core. All right. So what do we do when we have some sort of non-uniformity in the superconductor? Instead of BCS, we talk about BDG. So we solve the BDG equations. BDG equations are simply is integral h x prime psi x prime is equal to some eigenvalue e psi x. Okay. And I'm not going to give you the steps, but if you want to solve the this eigenvalue equation for a zero energy eigenvalue, then of course you have to put e equal to 0, and then for let's look at rho less than xi. Okay, and I'm going to solve the BDG equation for this Hamiltonian. This is the BDG equation. I'm going to solve it for rho less than xi and rho greater than xi, and then I will match the solution just like we do for ordinary Schrodinger equation. For rho less than xi, it's simple because delta 0 equal to 0. There is no vortex, and there is no order parameter. So all we have is really this grad square in the Hamiltonian. But I have to write this grad square in the polar coordinates. So the BDG equation will become minus 1 by 2m, and then del 2 del rho 2 plus 1 by rho del L rho. I'm just writing the grad square in polar coordinates times 1 by rho square del 2 del theta 2. So that's minus grad square by 2m minus mu. And then I have sigma z. If you notice, there is a sigma z here, sigma z. This is a 2 by 2 matrix. So I write phi x here. So this is a phi x is a spinor. is equal to 0 because I'm solving for a zero energy state. So phi x is uv. Now, if I'm solving for zero energy state, I also assume that the angular momentum operator L, which is minus I del L theta in 2D spherical in polar coordinate, I'm going to assume that this angular momentum operator have eigenvalue 0. Okay, so which means I'm going to put this equal to 0. Okay, the remaining equation is nothing but ordinary Bessel equation of order 0, as some of you may even remember. I mean, this is an ordinary Bessel equation of order 0 for both u and v. It's the same equation for both u and v, because all you have in the sigma z, you have an extra minus sign, but since the right hand side is 0, that minus sign is not going to matter. So it's this ordinary Bessel equation of order 0 for both u and v. So the solution is going to be phi rho is a j0 in some argument to m mu rho and chi. So chi is a constant spinor. You can take chi to be 1 1. Mu is of course positive. Okay. This whatever I said applies for mu greater than 0, and j0 is the solution of the ordinary Bessel equation of order 0. So j0 is the Bessel function of the first kind. So this is the Bessel function. There's a reason why I'm talking about these functions. So this is a Bessel function of first kind of order 0, and the Bessel function of the second kind, okay, that diverges at rho equal to 0, and therefore we ignore it. So that's the solution for rho less than xi. For rho greater than xi, now I have, of course, I have to take into account the delta. So there's going to be off diagonal elements in the Hamiltonian. Okay, there's going to be off diagonal elements in the Hamiltonian. But we can do some manipulations. Eventually, we'll see that the solution is going to be phi rho is b. So phi rho will still satisfy the the Bessel equation of order 0. Okay, you can show it. I mean, I'm not going to reproduce those steps. They are there in that paper. So the solution is going to be b j naught kappa rho plus c y naught kappa rho. I'm not going to define the kappa and so forth. I mean, those are just details. And you have done these type of things while solving Schrodinger equations. Times you have exponential I pi by 4 minus delta naught by Vf rho and 1 minus I. So now it's not just 1 1. I mean, it's 1 minus I. You need to have these type of phases, and I'm not going to go get into the details of why. Now, so this is the same as that. This is the Bessel function of first kind of order 0, but now you have the Bessel function of second kind of order 0 as well. Both of these are well behaved for rho going to infinity. So therefore, you have to include both. That's actually important. So you might think that I'm wasting time on these special functions and so forth, but I need to go through this to make an important point. All right, so now we have the solutions for both regions. I have to match the solutions and their derivatives at rho equal to xi. Okay, so if I match the solutions and the derivatives at rho equal to xi, I'll get two equations. And then there is also the normalization in the entire space that will give me a third equation. And how many constants I have? I have A, B, and C, and I have three equations. So I can uniquely solve for A, B, and C. Okay, and this I'm not going to solve. I mean, I'm going to actually write down the solutions, but this can be done. And this proves that an E equal to 0 solution is possible for a px plus ipy order parameter, okay, or 2D px plus ipy superconductor. I'm not talking about spin because it's spinless. 2D px plus ipy superconductor does have a zero energy solution, provided mu is greater than zero. That's actually important. Now let's take the situation where mu is less than zero. So let me backtrack. Before I do that, before I take the case mu is less than zero, let me also write down the second quantized solution corresponds to this second quantized operator that corresponds to this zero energy solution. So the second quantized operator then is going to be for the zero energy state is going to be, how do you do it? I mean, you get these phi. So I said phi is ux and vx. Okay. So all you do is really you take d2x and then ux c dagger x. Now there is no spin, so ux c dagger x plus vx cx. Okay. And if you notice, if you just look at this solution, this entire thing gives the magnitude of u and v. So mod u is actually equal to mod v. Okay, but the phases are different because you have this minus I here. So if you look at the phase, so ux has a phase, which is e to the power I pi by 4 and 1. But Vx has a phase which is e to the power I pi by 4 and minus I. So these I can write as e to the power I pi by 4 and e to the power minus I pi by 2. So that's minus I. So this is actually equal to e to the power minus I pi by 4. Okay. So therefore this gamma 0 dagger is equal to integral d2x and then mod ux e to the power I pi by 4 c dagger x plus for mod vx I can write mod ux and then e to the power minus I pi by 4 and cx. So because there is no spin index, you can easily check that for this operator, if you write the gamma 0, then of course this will change to e to the power minus I pi by 4, this will change to c, this will change to e to the power I pi by 4, and this will change to c dagger. So gamma 0 will in fact be equal to gamma 0 dagger. So a Majorana fermion excitation exists at the vortex core of a spinless 2D px plus IPO superconductor for mu greater than 0. What happens when mu is less than 0? That's actually important for those of you who want to learn this subject. Is important to understand. What happens when mu is less than 0? You can go back and do the same manipulations. Okay, I'm not going to do them anymore. I'm just going to describe what happens. If you have mu less than 0 now, okay, this equation will turn into not the ordinary Bessel equation, but it will turn into the modified Bessel equation of order 0. Okay. Now, and that will be the same also for rho greater than xi. So modified Bessel equation of order 0 has the property that it has a modified Bessel equation of order 0. This has two solutions, I0 and K0. Okay. But the solutions has a property such that for rho less than xi, the phi rho is, I can introduce another constant, g times I rho times, square root 2m mod mu rho and times some spinor. And here I ignore k naught because k naught blows up at rho equal to 0. And for rho greater than xi, I'll have phi rho equal to another constant h, but k naught square root 2m mod mu rho, and then some other constant spinor. Here also I have only one solution because modified Bessel equation has the property that now I naught blows up for rho going to infinity. Okay, this was not the case previously. For the ordinary Bessel equation, both solutions are actually well behaved as rho goes to infinity. So for rho greater than xi, I in fact had two constants, but now I have just one. So what is the consequence of that? The consequence of that is that now I have two unknowns, g and h. But how many equations? I still have the continuity at rho equal to xi and the equality of the derivative and the normalization. So I have three equations and two unknowns. So my set of equations is overdetermined. The constants are overdetermined. And if you have that kind of a situation, the number of equations is greater than the number of unknowns, then that indicates that there is no solution for generic values of the parameters. Okay. And that shows you that mu greater than 0, you have a Majorana fermion. And for the 2D px plus IPY state, this state is called weak pairing state. That's the nomenclature that is there in the Reed and Green, a very famous paper. Weak pairing state, mu less than 0, no Majorana fermion. This state is called strong pairing state. Okay. The reason these are called weak pairing and strong pairing is because you can show that if you write down the superconducting order parameter in real space, x1 minus x2, then in the weak pairing state, it goes like an algebraic, it's an algebraic fall off. So it's x1 minus x2 with some exponent there. And in the strong pairing state, it's an exponential fall off. So that's why these are called weak pairing and the strong pairing state. And one of them is topological, the other one is not. And so there is a transition, therefore, as a function of mu. Okay, that's actually an important point because we're going to exploit that transition as a function of mu when we design some sort of a realistic system in which these types of things can play out. We can actually get a Majorana fermion. So we can tune mu to get into the correct state. So are you guys still there or did I get disconnected?
Very much there.
Okay, all right. So I'm going to switch gears now. So is there any question on this stuff? I mean, I wanted to introduce this because this concept of weak pairing, strong pairing, a phase transition as a function of mu. So these two phases will actually be separated by a topological quantum phase transition as a function of mu. You can, these are concepts that people talk about. They were first introduced by Reed and Green in the famous 2001 paper. And some of you may already know about that paper, Reed and Green, 2001 PRB. But they did not have this explicit solution of the Majorana fermion. Any questions?
So
I'm going to switch here now.
Yes, so the mu is something like chemical potential. One can tune. Is that
mu is the chemical potential? Mu is the chemical potential. Yes.
Okay.
Yeah. Sorry, I should have mentioned it. Mu is the chemical potential, as you can see in the Hamiltonian here. Okay. All right. So therefore we have. So I said that you have spinless 2D spinless px plus IPY superconductor. If you have vortices, then the vortices will have localized Majorana fermions, zero energy states. So I can have a bunch of before I get into a bunch of vortices, let me now now that we know that I have a vortex in a 2D px plus IPY superconductor, I have a localized Majorana fermion quasi-particle associated with it. There's going to be other quasi-particles associated with the vortex as well. Those are the Caroli, DJ, and Matricon states appropriate for the vortex of a px plus IPY superconductor. But below all those quasi-particle states, there's going to be an exactly zero energy state, which would be a Majorana fermion. In contrast, if you have a 2D S-wave superconductor, even ignoring spin, I mean, spin is an additional problem. But even if you did, well, okay, I mean, if you did not have spin, then you cannot have an S-wave superconductor. But suppose I ignore the spin and just write down the BDG equation without that Px plus Ipy in the delta, you could show that the lowest energy Caroly-Dijen matricon state that you can solve within the vortex, just the way I did, that does not have a zero energy solution. So within the vortex there, the lowest energy state will be delta square by epsilon f, of the order of delta square by epsilon f. So in other words, this is not going to be, this S-wave superconductor does not support a Majorana fermion in the vortex course. In order to do that, you need a special type of BDG equation that's only provided by Px plus Ipy type of order parameter. Now, if you have, let's say, that kind of a zero energy state in the spectrum, okay, so you have a spectrum, you have a bunch of states, so this is E equal to 0, and you have, so this is, we're talking about a superconductor, so therefore the excitation energies come in plus minus epsilon pair. So you also have a bunch of excitations on the other side. Okay, but you have only one solution, let's say at E equal to 0. I mean, as someone very intelligently asked, I mean, you cannot really have a single solution, but suppose the other solution is physically far away, spatially far away. So if I just focus on one part of the system, this is what I get as the excitation spectrum. The important point here is that it is almost impossible to get rid of the state at E equal to 0 in this type of a situation. This is topological protection. Why is that? Why? I mean, what is the origin of this topological protection? There are several ways one can describe this, but the one that I like is the following. The argument that I like is the following. Suppose by applying some perturbation, some continuous perturbation, okay, you could remove the state at E equal to 0 and turn it into a state at E equal to some plus epsilon. So E equal to plus epsilon. So you have removed the state. You cannot really destroy because the total number of eigenvalues must be conserved of a set of differential equations for continuity purposes. And if you have a continuous perturbations, so suppose you remove it and turn it into an E equal to plus epsilon eigenvalue. Well, but because it's a superconductor, there's a particle hole symmetry that guarantees that if you have an excitation at plus epsilon, you must also have an excitation at minus epsilon. So that tells you that you need also have an excitation at minus epsilon, which means the number of eigenvalues of this set of differential equations changes by 1. Okay. Now there is a corollary in the Sturm-Liouville theory of solving differential equations, that by applying small continuous perturbations, you can deform the eigenvalues, okay, but you cannot change the total number of eigenvalues. And because there is just one E equal to 0 state appearing here, you cannot really get rid of it, because if you, as I said, if you did get rid of it at plus epsilon, you would need to increase the number of eigenvalues by 1, because you have to have another state at minus epsilon. And so therefore, this E equal to 0 non-degenerate eigenvalue is robust. Well, you might say, well, this is not strictly an E equal to 0, just single E equal to 0 eigenvalue. There's another one, but that one is far away. Okay, and that state, that one indeed can mix and split. So a pair of Majorana fermions can indeed mix and split to plus epsilon and minus epsilon, which is why in order to see Majorana physics and topological quantum computation and so forth, you need to keep the pairs far away from each other so that they do not have any overlap. Okay. All right. So that's the concept of topological protection. That if the other Majorana fermions are far away from a given Majorana fermion, then you cannot really get rid of this Majorana fermion by small continuous perturbations. That's topological protection. Let's talk about non-abelian statistics. So this was topological protection. Now let's talk about non-abelian statistics. Why people talk about Majorana fermions for topological quantum computation or quantum computation. Now, how much time do I have? How are we doing with respect to time?
So we have 25 minutes more.
25 minutes. Okay, that should be good enough for what I want to do. Is there any question so far, other than the ones we had?
So Manipal Singh was supposed to ask a question, and Prakriti Neha. So you may please
Sure.
unmute and ask.
So my question is that
Yes.
in a 2D spinless px plus ipy system, we have Majorana fermions in the vortex core.
Mm-hmm.
So they are spatially separated or not?
Yes, they are. So these are
In the
single. These are single. So if you have just a single vortex in a 2D px plus IPV superconductor, if you have just a single vortex, then that single vortex will have a single Majorana fermion. So the solution that I gave you is for a single Majorana fermion. A pair of Majorana fermion is trivial to get, because I mean a pair of Majorana fermion on top of each other is or overlapping each other is kind of trivial to get, because an ordinary fermion can be viewed as a pair of Majorana fermions.
yes, sir. And so can you go to previous page?
Mm-hmm. Oh, go to previous page. Okay.
So the gx1x to the function
G or
x1
G R1 minus R2. Oh, this one, yeah.
yeah, gx1 minus x to the function.
These
Can
are
you tell the first one is for weak pairing state and the second one, which is exponential, is for strong pairing state?
Yes. So these are so the pair wave function here falls exponentially quickly, which means the pairs are tightly bound.
Okay. But for weak pairing state, we have the power law behavior.
Yes. Yes.
Okay, so there's the weak coupling between the pair.
Yeah, I mean you can think of that. In the cold fermion literature, you can have fermions, and the fermions can create a BCS type superfluid, but also the fermions can make like molecules. If they interact strongly with attractive interaction, they can form molecules and then post condense. So there is BCS to BEC transition in a fermion, in the fermion system in the cold fermion literature, and those transitions have been observed. So it is similar to that, and Leggett actually showed that you can describe the BEC by using the same BCS type treatment, but simply taking mu negative. Okay, mu negative means the pairs are tightly bound like molecules. Okay, and then those molecules both condense.
Okay, and if we go to the mu less than 0 resign to mu greater than 0, will it change the topology?
Yes, these are two topologically distinct states. Mu greater than 0 is the topologically non-trivial system that for px plus IPO superconductor that host Majorana fermions. The mu less than 0, the strong pairing state, is the topologically trivial one that does not have a zero energy solution, as I showed here.
Yeah.
That does not have a zero energy solution. So these two phases will be separated by a topological quantum phase transition. There must be a topological quantum phase transition separating these two phases. By the way, there's one other point that I forgot to mention here. So I said that if you have a single localized zero energy state in the spectrum away from other zero energy states, then that zero energy state is extremely hard to get rid of by continuous perturbation. That's topological protection. In fact, the only way you can get rid of this type of E equal to 0 state is by making the system go through a quantum phase transition. Because in a quantum phase transition, the gap collapses, which means there are many other states, all of which come to zero energy. Okay, so this conservation of the zero energy eigenvalue, that breaks down. So on the other side of quantum phase transition, you might get into a state where there is no such zero energy state. Okay, so the concept of topological protection tells you that as long as the gap is intact, you cannot get rid of this single non-degenerate, spatially isolated zero energy states from the system. But of course, if you have a topological quantum phase transition, then infinite number of zero energy states are created at exactly the quantum critical point, and then there is no, all bets are off. There is no conservation. So that's the way to get rid of topologically protected zero energy states.
And so one more question, that in spinless 2D system, the vortex is itself on the surface.
No, you can create a vortex in the bulk by applying a magnetic field. But remember, that's an artificial system, because I talked about a spinless 2D px plus IPR superconductor. If you had spins, then of course so these are arrows, these are not spins. If you had spins, then you would have this up spin and down spin there. And then you are not going to have gamma 0 equal to gamma 0 dagger, as you can check yourself.
Yes, sir.
Okay, so I did not have those spin indices here, but that is of course not physical. Physically, of course, you have spin.
So it's hard to realize Majorana fermions even in real 2D system also.
Yes, that's why there is so much research as to how you can get Majorana fermions.
Thank you, sir.
Mm-hmm. All right.
Hello, sir.
I mean, yeah, go ahead.
Hello, sir.
Yes.
Sir, in 3D topological superconductors, say copper dope bismuth selenide, strontium dope bismuth selenide, they were found like presence of conventional superconducting pairing symmetry as well as unconventional superconducting pairing symmetry. So for as it's like defined like px plus ipy being a spinless 2D feature, how much do it satisfy in this situation, like experimentally getting both the features?
Say it again. So, can you please? Also, there's a little bit of sound going on, so maybe there's some disturbance from. Is there a way somebody can mute so that sound goes away?
Anupam,
Okay,
can you unmute everyone?
Yeah, you can write, Prakriti, if you can write, because there is some background also coming.
Okay.
Okay, but yeah, but this is fine. I mean, if you cannot get rid of it, that's fine. I mean, you can just repeat the question one more time.
Sir, I'm telling that for topological superconductors like copper intercalated bismuth selenide and strontium intercalated bismuth selenide, experimentally the conventional superconductivity as well as unconventional superconductivity is experimentally probed. So in general, like suppose it is expected like px plus ipy sort of superconductivity could be there, pairing symmetry could be there, but as it is defined for the like existence of Majorana fermions as well, which are essential for getting superconductivity in topological superconductors. So how do it satisfy like being spinless 2D px plus ipy sort of feature in 3D topological materials?
Well, that's a difficult question to answer because it's kind of not that intuitive. But I'm going to address those questions in the next tutorial when I talk about actual physical systems where you can somehow satisfy gamma dagger equal to gamma. Okay, I mean those systems clearly have spins because no physical superconductor is without spin. But it turns out you can have right kind of uh, order parameter, and you need to introduce other elements as well, like spin orbit coupling and so forth, which will conspire to give you the right type of quasi particle expression, D dagger and D, such that D will turn out to be equal to D dagger. But it's kind of difficult to explain it in an intuitive, simple way, unless I actually write down those operators. Okay. All right.
Thank you.
Okay. Let me move to this idea of non-abelian statistics, and hopefully we'll be able to finish it. And then in the next tutorial, we'll start with physical system. We'll start with Kitaev model, this the model of 1D P-wave chain, and then we'll introduce the superconductor semiconductor heterostructure that we introduced, on which there has been lots and lots of experiments now, and have been big claims of people actually realizing Majorana fermions. I'm not going to touch upon the copper doped bismuth selenide and those types of topological superconductors, because I mean those types of topological superconductors, the ones that I'm going to talk about, this semiconductor superconductor heterostructure, that's also a topological superconductor, and in fact the most well-studied topological superconductor. But copper doped bismuth selenide, etc., those are systems I don't fully know, and they have not been that successful. The only other type of superconductor that there have been claims about observing Majorana fermions in vortices are in fact iron-based superconductors. But I'm not going to talk about those as well, because this is a big topic. If I want to go through sort of slowly with making everything clear and so forth, it's going to be impossible to cover everything. But hopefully, when I talk about this semiconductor superconductor heterostructure, you will see what I'm talking about, how you can, in fact, satisfy gamma dagger equal to gamma or D dagger equal to D, even in the presence of spin. And what are the things, ingredients that you need to be able to do that? It's not that it's simple. It's a bit complicated, but we'll talk about it in the next tutorial. Today's tutorial is basically to explain the concepts which are not usually explained or even brought upon in a conventional talk, but these are absolutely crucial for you to understand. And it's kind of difficult to understand, non-abelian statistics, for instance. I mean, you can probably understand in some qualitative manner, but I'm going to try to give you some sort of a solid understanding of what this is. So, non-abelian statistics. So I'm going to follow a paper by Ivanov, PRL 2001. All right. Now, you know that the order parameter in a superconductor, it's a quadratic. So it's a quadratic function of the fermion fields, right? So delta star, for instance, delta star is CC, average of CC. So what this means is that if the phase of delta, delta is mod delta e to the power I phi, of course. If the phase of delta changes by phi, changes by 2 pi, so if phi changes by phi plus 2 pi, let's say, that means this quadratic, so these two fermions which are being multiplied with each other, the combined phase is changing by 2 pi. So this implies that psi, I should change them to psi, or let me Let me change the psi here from my notes. So this implies that C goes to e to the power I phi by 2 C. Then only phi will change to phi plus 2 pi. Did I say this right? No, hold on. That's not what I meant. Let me take it back. So what I meant is this. So if the phase of delta changes by phi, changes by some angle phi, then that means the single fermion operator, the phase of that changes by phi by 2, because delta is a quadratic function of C. Okay, and conversely, C dagger changes to e to the power minus I phi by 2 C dagger. I hope that's understandable to you, because that's crucial. All right. Now consider that you have a 2D spinless px plus IPO superconductor, and I know that vortices in such a system will have a Majorana fermion. Suppose I have 2n vortices. So I have 2n Majorana fermions, and suppose they are far away from each other, so they don't destabilize each other by mixing and splitting. Okay, so they are far away from each other, even though I did not draw them as far away from each other, but assume that they are far away from each other. So we have 2n Majorana fermions. Now I have been telling you that a pair of Majorana fermions will give rise to a single fermion operator. So you can define C dagger equal to gamma 1 plus I gamma 2. We have been doing this trick a number of times. Then C is gamma 1 minus I gamma 2, and so forth. So you can construct n fermionic operators out of 2n Majorana fermionic operators. And each one of these fermionic operators, C and C dagger, you can define these states. You can define these states 0 and C dagger 0, which is 1. These are, by the way, the two states of a qubit in a topological quantum computer. And these states are also at 0 energy, because these fermionic states that you have constructed, these are really superposition of 0 energy states. So those fermionic states are also 0 energy states. So it does not really matter if you put an electron in a 0 energy state. The electron will still have 0 energy. So what you have therefore created is n fermionic states, each one of which can be in two degenerate states, distinguished by the occupation number 0 and 1. Okay, so there is a 2 to the power n fold degeneracy, and all of this degeneracy is in the ground state, the state with 0 energy. I mean, just calling the ground state energy as 0 energy. So there is a 2 to the power n fold degenerate ground state. Okay, and I'm going to assume that this superconductor has a gap. Of course, all superconductors have a gap, and this superconductor also has a gap. And so therefore there is no other single fermionic excitations below the energy delta. Okay, so all these 2 to the power n fold degenerate ground states, remember where the degeneracy comes from. The degeneracy comes from the occupation number of these pairs of Majorana fermions, the fermionic operators that I could create by combining pairs of Majorana fermions, which are themselves far away from each other. Okay, so these fermionic states are also at 0 energy. But those fermionic states can be, each one of them can be in two possible states, 0 and 1. So I have 2 to the power n such occupation number states. Okay, each one of which are at 0 energy. So that's the 2 to the power n fold degenerate ground states, all of which are protected by this gap. That concept takes a little while to set in if you are hearing it for the first time. Those of you who know this, you know what I'm talking about. All right, and if this is unclear, please ask me. Now, I said that all these degenerate states are protected by a gap. So suppose now I I have those Majorana fermionic states at vortices, okay, and suppose so these are the states, and suppose I take one of them and move around another, but I do this adiabatically, which means I do it sufficiently slowly so that I do not mix with any of the states which are above the gap. Okay, so this is a transformation. I took one Majorana fermion and moved around another. So something should happen, but the only thing that happens, or that is allowed to happen, because I'm doing this adiabatically, is there is a unitary transformation in this space of degenerate states. And what is this unitary transformation? That's the question. Okay. All right. So let's think about this a little bit more mathematical terms. So we have associated with each vortex. How do you define a vortex? A vortex is an object around which the superconducting phase changes by 2 pi, right? So delta e to the power I phi, this phi changes by 2 pi around the vortex, right? So I can represent a vortex instead of phi changing continuously by 2 pi. Typically what one could do is one could associate a branch cut with a vortex. Okay, that's just a mathematical formulation of a vortex. One can associate a branch cut with the vortex across which the phase of the superconducting order parameter jumps by 2 pi. And so if you are away from the branch cut, then the superconducting phase is single valued. Well, I mean, phase is single valued, but this phase, as you rotate around the vortex, this phase changes by 2 pi. So if you rotate, like if you did not have the branch cut, if you come here, then over here, the phase will have two values. One when you just considering this angle, but the other one when you are considering this greater angle. So in order to get rid of this multi-valued phase, what one typically does is one introduces this branch cut, so you go to the other complex plane and so forth. That's the complex analysis. But anyway, so the point I'm trying to make here is that you represent a vortex and the phase change by 2 pi around the vortex by introducing a branch cut, and you allow the phase change by 2 pi across the branch cut, and the phase remains constant everywhere else. That's how you mathematically model a vortex. All right, so now let's say I have two vortices in a P plus IP superconductor, and you have the branch cuts associated with them. The branch cuts go all the way to infinity. So let's call them gamma 1 and gamma 2. Now what I'm going to do is I'm going to interchange their positions. So I have the two vortices. Each one of them comes with their branch cut. Okay. These vortices means these are also Majorana fermions. So now I'm interchanging their position, meaning I'm taking this one over here and this one over here. But you can stare at this, and in a moment you'll realize that when I do interchange, then only one of the vortex or Majorana fermion, let's say this one, this is going through a branch cut. This one is not going through a branch cut. Okay. So whenever the Majorana fermion is going through a branch cut, which is the case for this one, the superconducting phase is changing by 2 pi. So phi is changing by phi plus 2 pi or minus 2 pi. The effect of that on ordinary fermionic operators, I said, is C goes to C e to the power I pi. But what is e to the power I pi? E to the power I pi is cos pi plus I sine pi. This is 0, but this is minus 1. So C goes to minus C because of this phase change. Now, if you recall the Majorana fermion operators, they are after all composed of single fermionic operators, because Majorana fermion operators are nothing but some C dagger plus VC. So these are single fermionic operators. So if this Majorana fermion is moving across a branch cut, then, and if I call this, let's say this is gamma I, and this is gamma I plus 1. So as a result of this interchange, gamma I, so I define Ti, I define the operator Ti, okay? This is the interchange operator. This is the interchange gamma I and gamma I plus 1. I mean, by interchange, I mean interchange their positions. What you do when you talk about statistics, like you interchange the position of two fermions, the wave function gets a minus sign. Interchange the position of two bosons, the wave function remains unaltered. That's the interchange that I'm talking about. Interchange the position of two minor fermions. So Ti is the interchange operator. So the result of the Ti operation is that only one of them, the gamma I plus 1, okay, this is becoming minus gamma I. It's getting a minus sign. But gamma I, because it is not going through a branch cut, both branch cuts are over here. So the gamma I is not going through a branch cut. Gamma I is going to plus gamma I plus 1. So only one of them is acquiring a minus sign. And that's the important point. That's the crux of non-abelian statistics. And of course, every other minor fermion remains what it was for j not equal to I and j not equal to I plus 1. I hope this is clear. Why only one of them is acquiring a minus sign and the other one is not. Okay. Now, so now let me introduce an operator tau. Okay, tau is the operator that that gives you this transformation. In other words, so I want tau gamma I tau inverse equal to gamma I plus 1 and tau gamma I plus 1 tau inverse equal to minus gamma I. This is just the description that what happens with the interchange operation. But now I am talking about a quantum mechanical operator that gives me this effect on gamma I and gamma I plus 1. So what is this tau? I claim that this tau operator is 1 by root 2 1 plus gamma I plus 1 gamma I. Let me quickly check that indeed gives me, so this operator represents interchange of gamma I and gamma I plus 1. Let me prove that to you, that this operator indeed gives me this transformation. All right, so I said I need gamma, let's say tau gamma I plus 1 tau inverse. Okay, so that's 1 by root 2 1 plus gamma I plus 1 gamma I, and then gamma I plus 1. Let me change this to 1 by 2, and then 1 plus gamma I plus 1 gamma I. So then I have 1 by 2, and then let me multiply these together. So I'm going to get gamma I plus 1. No, so hold on. Well, look, I can do this, but let me do the other one first. This one. So let me change this to gamma I, and this also to gamma I. Yeah, this is fine. So I'm trying to prove this one first. So I have half. So gamma I plus 1, gamma I, and gamma I. So I just multiplied these, and I still have 1 plus gamma I plus 1 gamma I. But gamma I square is 1. So that's half gamma I plus 1, and then 1 plus gamma I plus 1 gamma I. So that's going to give me half gamma I plus 1 plus gamma Hold on. Oh, I made a mistake here. Hold on. So I forgot this one here. So let me take this back. So over here, I'm going to get half gamma I plus gamma I plus 1, gamma I, and then I have 1 plus gamma I plus 1, gamma I. This would be half, and then gamma I plus, so this multiplied by that is gamma I, plus this multiplied by that, so that's gamma I plus 1, gamma I, plus this multiplied by that, that's gamma I plus 1, gamma I square, plus, well, gamma I square is 1, so I can use that, gamma I plus 1, gamma I plus 1, and gamma I. So I'm just going to take another 10 minutes and then I'll be done. So it's equal to, so this is equal to half, and then this is gamma I. This is, oh, I guess I'm kind of
So
tired
you
now.
haven't
I didn't was you probably caught this already, and this is what comes out of tiredness. So this was a tau inverse.
inverse. You haven't inverted.
Yeah, this is a tau inverse, and that's where I'm getting confused. So tau inverse means I'm going to get a minus sign here. You can check that just take the tau and tau inverse, multiply them together, you see whether or not you get 1, and you will. So therefore, which one will have a minus sign here? So which of these terms will have a minus sign? This will have a minus sign. This will have a minus sign. So it's 1 minus gamma I plus 1 gamma I. So therefore, you have gamma I plus this will have a minus sign. This will have a minus sign because it's gamma I plus 1 gamma I. This is gamma I plus 1 gamma I square, and this one will have a minus sign. Minus, so you have gamma I plus 1, gamma I plus 1, gamma I squared is 1, gamma I plus 1, gamma I. Okay, now we're done. So it's gamma I minus, I can switch these two, that will produce a minus sign. So because these are fermions, so I'm going to get plus gamma I squared, gamma I plus 1, plus this is already 1, so that's gamma I plus 1, and this is gamma I plus 1 square is 1, so that's gamma I. So this and that cancel. This is equal to 1, so that's half, and 2 gamma I plus 1, so that's gamma I plus 1. So indeed, you can see that tau gamma I tau inverse is gamma I plus 1. And I'm not going to do this one, and you can just show it yourself. That will give you a little bit of practice. So therefore, the operator tau is this, the interchange operator. So tau is 1 by root 2, 1 plus gamma I plus 1 gamma I. Okay. I claim that this you can write, so this is the interchange operator. This you can actually write as exponential pi by 4 gamma I plus 1 gamma I. Again, that's actually quite simple to show. I mean, I'm just going to, let me just give you the first few steps. So this operator, you can write exponential pi by 4 gamma I plus 1 gamma I is 1 plus pi by 4 gamma I plus 1 gamma I plus pi by 4 square by factorial 2 gamma I plus 1 gamma I plus 1 gamma I, and so forth. You can write another term. So pi by 4 cube by factorial 3, and then this you have 3 of them, gamma I plus 1 gamma I plus 1 gamma I, and gamma I plus 1 gamma I. And this term, for instance, you can see that So let me just write this gamma I plus 1, gamma I plus 1, gamma I. So I can switch these two. That will give me a minus sign. So this is minus gamma I plus 1 square and gamma I square. So that's minus 1. Okay. So this one and that one gives me 1 minus pi by 4 square by factorial 2. And then I'm going to get other terms, when I include other terms. So this series will be sine of pi by 4. Oh, no, this is cosine. This is cosine of pi by 4. This series will produce a cosine of pi by 4 when you include all the terms in this exponential. And if you look at these terms, you have pi by 4 gamma I plus 1 gamma I, and you have this one, so that's pi by plus pi by 4 cube by factorial 3, and you can manipulate this. It's actually fairly easy. All you need to do is interchange these two. That will give you a minus sign. Then you're going to get minus, so this term will become minus gamma I plus 1 gamma I square gamma I plus 1 square gamma I. But these are 1, so that's minus gamma I plus 1 gamma I. So you're going to get a minus sign here. You're going to get a minus sign here, pi by 4 cube by factorial 3 and gamma I plus 1 gamma I. So you can factor out gamma I plus 1 gamma I, and you're going to get pi by 4 minus pi by 4 cube by factorial 3 plus so on, which will give you a sine pi by 4. So you can see that this is basically cosine pi by 4 plus gamma I plus 1 gamma I sine pi by 4, which is what you have, this 1 by root 2 times 1 plus gamma I plus 1. Anyway, so let me finish this. So t or tau, the operator that interchanges two Majorana fermions, you can write as exponential pi by 4 gamma I plus 1 gamma I. Those of you who are not following this, the students, they can come back and look at these derivations. These are easy, straightforward. But if you're just listening it for the first time, and if I'm going too fast, you can come back and look at them. All right, so that's the interchange operator. But now I can write them in the Fock space, because that's the space that we have been talking about, the degeneracy and so forth, in the space of these type of states for each pair. So now I have C operator. Remember, so these states C and C dagger are defined as C equal to gamma I plus gamma I plus gamma I plus I gamma I plus 1. This is how we are defining the C's. So you can write C dagger and C to gamma I minus I gamma I plus 1. So this is from single fermionic state or complex fermionic state or ordinary fermionic state that you can create out of pair of Majorana fermionic states. So then, if you have C and C dagger, and I've shown you before that, so something like this gamma I plus 1 gamma I, from this definition, this turns out to be I times 2 C dagger C minus 1. Okay, this I did when I talked about this delta function potential. You just have to write gamma I and gamma I plus 1 by inverting these equations, and then you'll get this 2 C dagger C minus 1. So anyway, so tau therefore will become exponential I pi by 4 and then 2 C dagger C minus 1. So now this operator 2 C dagger C minus 1, if you write them in this subspace of 0 and 1 states, then you have 0, 2 C dagger C minus 1 and then 1 here, and then 1, 2 C dagger C minus 1, and then 0 here, and then 1, 2 C dagger C minus 1, and then 1 here. So that is what? That is, this will give you minus 1. This will give you, this will be 2 minus 1, that's 1. This will be 0, and that will be 0. So this is minus sigma Z operator. So in this subspace of C and C dagger states, or 0 and 1, this interchange operator is basically exponential. So this is this. So it is exponential minus I pi by 4 sigma Z. Okay, all right. So that's good. So, but this is still this is still a diagonal matrix, and you know that the diagonal. So this is the effect on these 0 and 1 states if you interchange the location of these two Majorana fermions. Okay, but this is still a diagonal matrix. So where is non-abelian property comes from? Because you know that even if you get a matrix transformation, if you do this interchange, the transformation that are given by diagonal matrices is actually abelian, because diagonal matrices commute. But if you, and I'm not going to do this because there is not time, but if you have 4 Majorana fermions, let's say, and you can call them gamma 1, gamma 2, gamma 3, and gamma 4, you can define C and C dagger using these two, and you can define another fermion operator, C, D, and D dagger using those two. Okay, then you can get tau T1 if you interchange the two Majorana fermions in the same pair. That will produce exactly what we just did. It's minus I pi by 4 sigma Z. So it will be a diagonal matrix in this, you know. So now there's going to be, so your basis should be 0 and C dagger 0 and D dagger 0 and C dagger D dagger 0. So this 0 is the vacuum. Okay, these states have only one particle in these two fermionic states. This state has, you know, both fermionic states are occupied. So that's the basis. That's the basis of your when you write down this tau. So this would still be a diagonal matrix in this basis. So it'd be a 4 by 4 diagonal matrix. And in fact, the terms would be like you do a minus I pi by 4, you do I pi by 4, and so forth. Okay. Tau, if you define tau T3, which means you are so tau T1 interchanges this and that, and tau T3 interchanges this and that. That will still be a diagonal matrix, because again you are interchanging two Majorana fermions from the same pair. But tau T2, which interchanges this and that, so tau T2, okay, tau T2 means you are taking a Majorana fermion from a pair and you are interchanging with another Majorana fermion from a different pair. Okay, this you can, you know, using this Majorana algebra, you can calculate this matrix as well, and this matrix will turn out to be 1 by root 2, and then 1 0 0 minus I, and then 0 1 minus I 0, and 0 minus I 1 0, and minus I 0 0 1. Okay, I don't have time to go derive this, but you know, it will take a little, probably 10-15 minutes for you. You just follow the same method that I'm describing. So now that this is the crux of non-abelian statistics. So now you see that you are, all you are doing is really moving one vortex around another. Okay, these are from two different pairs, but remember these vortices are far away, or these Majorana fermions are far away from each other. But something is happening in the state such that you are getting from one set of occupation numbers of these fermionic states associated with these pairs of Majorana fermionic states, and you are getting into another set of occupation numbers. And that's what is meant by these off-diagonal matrix transformations. So this is actually extremely curious, because none of these Majorana fermions or these vortices are actually interacting with each other, because they are supposed to be infinitely far away from each other, very far away from each other. So all you are doing is you're really creating loops. You're really interchanging them in space, but making sure that they are far, far away from each other. But while you are doing that, there is some unitary transformation that is going on in this degenerate subspace of ground states, such that you are going from one ground state where you have one set of occupation numbers, and you're getting into another set of occupation numbers. So the electrons actually moving in and out of the condensate and giving you a different set of occupation numbers. That's what is meant by this matrix transformation. This is an off-diagonal matrix in the subspace of occupation numbers, in the basis of the occupation numbers. Okay, and this is non-abelian statistics, because these are off-diagonal matrices. So if you move interchange 2 and 3, and let's say you have another pair and you interchange 4, so you have another pair, so you interchange 2 and 3, which will be one off-diagonal matrix transformation, and you interchange 4 and 5, and that will be another off-diagonal matrix transformation. There is no guarantee that if you 4 and 5, if you interchange 4 and 5 first and 2 and 3 second, these two operations will commute, because now we are talking about operations by matrices which have off-diagonal elements, and you know that matrix multiplication with off-diagonal elements do not necessarily commute. And this is non-abelian statistics, but this is purely statistical effect. The Majorana fermions or the vortices are not actually interacting by any sort of interaction like Coulomb or anything else. Okay, and these unitary transformations can potentially be used to create quantum gates. So those 0 and 1 states of these fermion operators are the qubits. And you are operating in this state of qubits, you are unitary transforming these occupation numbers, meaning these different states of qubits, by only taking vortices or Majorana fermions around each other. So it does not really matter if there are local perturbations to your these loops. And so you have topological protection of the qubits. So it will be some sort of immune to noise, the 0 and 1 states of a qubit. That's the topological protection that I talked about before. But also these quantum gates, you have this unitary transformation on these states of the qubits. These are basically statistical transformations. You have a pair of bosons, you move around, or a pair of fermions, you move around each other, you pick up a minus sign. That minus sign does not care if your loop had some perturbations. As long as you moved around each other, you pick up a minus sign. This is similar. These transformations will happen no matter if your loops are deformed by your computation process, by however you are moving them. These unitary transformations will happen. So these quantum gates are also topologically protected. So this is topological quantum computation using Majorana fermions in a topological superconductor. Okay. In the next tutorial, I'm going to start talking about physical systems. But before that, I'll start with Kitaev model. Okay, and then we'll go over the physical systems, superconductor, semiconductor structure, talk about experiments, the important experiments that have come out, and so forth. Yes.
Yeah. So thank you, Sumanta. It was a wonderful tutorial, and I think you have exposed us to a lot of questions that we always had in mind. But next time, whenever on 5th March when we meet, I hope you are going to also, which didn't become very clear to me yet, that what is the experimental proof, because you in between said that copper-based bismuth selenide do not seem to have Majorana fermions, possibly. That's
Well,
what you mentioned. Yeah, but so what is the experimental proof that you have Majorana fermions? If you can touch upon that next time,
no,
that would
so
be really useful.
so the next tutorial will be entirely on those.
Okay,
That
fine. That is,
this tutorial was basically the mathematical background and various concepts that are often talked about. But the copper doped bismuth selenide, I mean, they are supposed to have Majorana fermions. The question is whether or not they have been absorbed.
yeah.
So
So,
far, the only system where there are claims of observation of Majorana fermions are these semiconductor superconductor heterostructures.
yeah, I remember that you mentioned in that talk also, earlier talk also. So I think that is, but why? I mean, what? I think it will become really good if you can tell us why you are saying. I mean, although it is being claimed that you have Majorana fermions in these selenides also, what is the doubt? Like, what exactly is experimentally lacking that one is not able to prove that this is what, this is
Yeah,
why?
that's
So
a
that,
very important. Yeah, that's a very important question. And
yeah.
so you're basically asking what is the smoking gun signature of Majorana fermion and why has not that been absorbed? I
Yeah.
mean, just to give you a simple one line.
Hello?
Can you hear me? Yeah.
Your voice broke actually in between.
Oh, okay. So just to give you a one line answer to that question is that most of these experiments they concern zero bias tunneling peak. So you probe the topological defects by tunneling conductors. Now you get a zero bias peak. Now the problem is the zero bias peaks can appear because of other reasons as well, other than there is a Majorana fermion there. Okay, so to conclusively prove that this particular zero bias peak is from Majorana fermion and not from other reasons like disorder or their weak anti-localization, that is most of the research is about, and no one has actually been able to prove conclusively that this. So in order to actually conclusively prove this Majorana fermion, you need to do something more than tunneling conductance peaks.
Okay, so that's sort of okay, fine. So one should, okay, fine. So it was really very lucid talk, and there were many things. Of course, I don't claim that I have understood everything because I don't think I have a proper background also, but it clarified a lot of things which we read and we kind of skip. That understanding has come little better. So thank you so much for taking your time and sharing your ideas and thoughts with us so that we can understand things better.
Okay.
Thanks a lot.
And for the experimentalists, so this talk was mostly geared toward the students, but for the experimentalists in the audience, the next talk would be much more, a normal physics type of seminar or colloquium or discussion of more physics and experiments and so forth.
That would be really nice. But this was also good because it was important. Because many a times when you read theoretical papers, you skip many things because you don't understand. But now at least one has started getting to the point where you can see what it is related to. So I think it was really useful. Thank you so much, and thank you all the participants.
Thank you.
We'll just come back together once again on 5th of March, the same time. Thanks a lot.
All right. Thank you very much.
Bye.